Well, hello all. We're going through the paper and we are going to have a look at past papers, and we're going to deal with question number 5. Ooh, everybody hates question number 5, the work-energy theorem. Or do you? Maybe you love it. Maybe you're a masochist. Who knows? Question 5. Okay, work-energy theorem. We're working through from 2020 to 2017's papers. Let's have a look at last year's work-energy theorem. A roller coaster car of mass 200 kilograms, there it is, with the engine switched off, travels along track ABC, which has a rough surface. Okay, there's friction as shown in the diagram below, which has a rough surface as shown in the diagram below. At point A, which is 10 meters above the ground, the speed of the car is 4 meters per second. At point B, which is a height h above the ground, the speed of the car is 2 meters per second, so it's got slower. During the motion from point A to B, this number of joules of energy is used to overcome friction. Okay. Ignore rotational effect due to the wheels of the car. Define the term non-conservative force. Okay, non-conservative force depends on the path of the force for the work which it does. So in this case, it's the friction. So in your answer is something to do with it depends on the path taken by the force that will affect the work. So a non-conservative force in this case is friction. I would go and look at the memo. I'm not good at definitions. I would be an expert if I was writing the exam. I would go and look at the memo. Okay, same place you find these papers. Calculate the change in the kinetic energy of the car after it has traveled from point A to point B. So here it's going 4. Now you know that they're going to give you the mass of the car. So you need a formula for kinetic energy. What's that formula? Half mv squared. So half times 4, which is 2, half times 4, which is 2 times 200, half mv squared. Okay, so let's do that again. Half of the mass is 100 times v squared is 1600 or 1600 joules of energy to start off with, and then you work out the kinetic energy there, half mv squared. So what is the question? Calculate the change in kinetic energy of the car. Okay, so you subtract that half mv squared from that, and that's the change. Always the final energy minus the initial, so it's going to be less. It's going to be a minus answer. Use energy principles to calculate the height h. Okay, use energy principles to calculate height h. So we're going to use something like, do they give us the friction? Yes, they give us this. So we're going to use one of those formulae that are associated with the work-energy theorem. And if they give us the friction, then let's look for those formulae on our data sheet. They give us the friction, so we must know where to find this. So let's find it. Work net is change of kinetic energy. And all this work NC, which is your friction, non-conserved, work non-conserved is change of kinetic over change of potential. So if we've got to work out the height, we're going to have, we know already the change of kinetic, we worked that out. And now we're going to work out the change of potential. So they give us this is the frictional force. Don't forget it's a negative. Change of kinetic energy, remember that's a negative, and then we're going to work with this, which is our change of potential energy. Now, change of potential energy is also somewhere here. Potential energy is mgh, or that formula. Do they give us a change of potential energy? Anyway, it's final potential minus initial. So I don't see it here. So let's go back to the problem. So we're going to use that work non-conservative, sorry, this one here, use energy principle, work non-conservative, which is this here, those joules, that's minus, equals change of kinetic, which is this answer, and then to calculate the height, mgh final minus mgh initial, and that's how we're going to work it out. So we're going to use that formula, work non-conservative equals change of kinetic plus change of potential, and that looks easier enough. Just always, you're must make sure that your negatives and positives are, keep track of them. On reaching point B, the car's engine is switched on in order to move up the incline. So now we have a force applied to point C, which is 22 meters above the ground. So let's suppose we calculate H, and then it goes from H to 22 meters above the ground. While moving from point B to C, the car travels for 15 seconds at a constant speed of 2 meters per second. Okay, so this should be highlighted. So now if it's moving at a constant speed, we know that the forces are balanced, while the average frictional force of 50 newtons acts on it. Okay. So what are they doing? Calculate the power delivered by the engine to move the car from point B to point C. So from point B to point C, the car travels for 15 seconds at a constant speed of 2 meters per second with an average frictional force of 50. Calculate the power. So we're going to now again use our formula, one of those formula, and we're going to use the Work-Energy Theorem formula, which is work net equals change of kinetic energy. Okay. Now, if it's traveling at a constant velocity, what's the change of kinetic energy? Remember, kinetic energy is half mv squared. But if the v is not changing, the m's not changing, the half's not changing. So we're going to say the net work is equal to change of kinetic energy, which is, you're going to write this all out, which is change of kinetic energy is 0. So now we know the network is going to be equal to 0. So what is the network done on this? What work is done on this trolley going from there to there? There's frictional work. So there's a force times a distance. So there's frictional work. Is this trolley going up? Yes, it's going from whatever with that height we worked it up to this height, 22. So there's going to be work done in overcoming gravity. We've got change the work, the change in potential energy. So the only things that we have to worry about are friction and change of potential energy. So, and then there's applied work. All of those are going to work net, are going to be part of our work net. Okay, so to calculate the power, we write the Work-Energy Theorem. Work net equals change of kinetic energy, which is 0. Now we start listing all the works. And what have we got? Travels for 15 seconds. So with an average frictional force of 50 newtons. So how are we going to convert that 50 newtons into work? We don't know distance because force times distance equals work. If we knew the distance, so how are we going to convert that frictional force into a work? Could we work out, what can we work out? Okay, we can work out the change of kinetic, of potential energy. So whatever that height was, which we calculated there, we subtracted from 22, and the change of height is mgh. So that is the one work. Now, how do we they give us a time? Oh, and a speed. There's the trick. There is the speed. So there's a speed. So if you take speed, which is 2 meters per second, you multiply it by seconds, you get a distance. There we go. So there's our distance. So we take velocity times time equals distance. So 15 times 2, it travels 30 meters. So that was the trick. So it travels 30 meters times, so force time, there's the force, times the distance, which is 30, cos 180, because that is negative. So there is our total work done by the frictional force. It's going to be force, which is 50. Don't forget it's a minus force, negative 50, times distance, which is velocity times time, which is 30. 50 times 30 times cos 180, which is going to give us a negative answer. So say we know that the work done by friction, we know the work done in going from H to 22 is mgh, so we know the work there in raising it, we know the frictional work, we know, and then those two works, work net equals change. So the network done by the engine must overcome those two that we've just worked out. This negative frictional work, and the car going up the hill is m times g times 22 minus h, and that's a negative work as well because it's going against gravity. So it's, I always say mgh cos 180. So those two negative works are going to be add up to, you add them both up and they add up to the work done by the car. Now you know the work applied by the engine. How do you change work into power? Well, you've got to multiply. Power is work done divided by time. They told us it travels for 15 seconds. So you now know the work by the engine. You divide it by the 15 seconds and you get the power of the car. So this was actually quite a difficult and challenging problem. I hope that you all got how we did it. So if not, replay this video. And this was quite challenging. Let's just see what 2019's Work-Energy Theorem problem is. An object of mass 1.8 kilograms slides down a rough, so it's sliding down a rough curved track and passes point A, which is 1.5 meters above the ground at a speed of that. The object reaches point B with the speed of that. Okay, define the term conservative force. So a conservative force is one in which the path taken does not matter in determining the energy that the force delivers. So the path does not matter. Again, check your definitions. Name the conservative force acting on the object. It's gravity. Okay? A non-conservative force would be friction. Is mechanical energy conserved as the object slides from point A to point B? Well, mechanical energy is the sum of the kinetic and potential. So does that change as it gets to the bottom? Well, if there's friction, it must change, I guess. So the answer would be, is it conserved? No, because there is a non-conservative force of friction. They tell us that this is rough, and we can see that it's rough. So the sum of the potential and kinetic energy at the top is not equal to the sum of the potential and kinetic at the bottom. Calculate the gravitational potential energy of the object when it was at point A. Okay, so what is gravitational potential energy? It's equal to mgh. Mass 1.8 times 9,8 times 1.5, and there's your gravitational potential energy when it's at point A. Look for a formula on your data sheet, but anyway, gravitational potential energy U equals mgh. You always give a formula. Using energy principles, calculate the work done by friction on the object as it slides from point A to point B. So you're going to again use one of the two formulae, and they're asking you to find friction. So why don't you use the formula work NC equals change of kinetic over change of potential. So you've calculated its potential there. It's got 0 potential at the bottom. So there's the change. The final is 0 minus whatever this m, which is 1.8 times 9,8 times h, which is 1.5. So that's your change of u. And then your kinetic energy, there's its velocity to start. There's its velocity to end. So what's the change of kinetic energy? It's going to be final for, it's going to be a half times m, 1.8, times 4 squared. That's the kinetic energy at the bottom. There's the kinetic energy at the top. Same formula. Subtract the 2, and then you're going to get your answer, as I say, using this formula for, work non-conservative is change of kinetic plus change of potential. So whatever the changes were, you add the 2 changes, just keep your positives and negatives, keep control of them. There's your friction led to the change of those 2. Okay, so that was easy enough. The only place you're going to get screwed is if you're going to get positive and negatives wrong. So you've done that. Surface BC in the diagram above is frictionless. So B to C. Okay, so B to C, now it's got a certain amount of energy and it's traveling at that speed. What is the value of the net work done on the object as it slides from point B to point C? So if there's no friction, it's just going to keep on going at 4 meters per second. So there's no net work done on it. None. Okay, net work is change of kinetic energy. Work net equals change of kinetic energy. There's going to be no change of kinetic energy. Therefore, there's no net work. Not going to change its velocity. 1 mark. Okay, so that was really simple compared to the next year's paper. Let's look at the 2018 paper. The diagram below, not drawn to scale, shows a vehicle with a mass of 1,500 kilograms starting from rest at point A at the bottom of a rough incline. Point B is 200 meters vertically above the horizontal. Okay, the total work done by force F that moves the vehicle from A to B is in 90 seconds is that number of joules. Okay, so where is force F? So there must be some applied force that is moving this vehicle up against friction and against height. So is force F a conservative force? So, okay, first of all, define the term non-conservative force. Non-conservative force is like friction, where it depends on the pathway taken by the force. Is force F a conservative force? It's an applied force. I would say no, because although you're working against gravity, the only conservative force I know is the work done by gravity, not by an engine. Calculate the average power generated by force F. Okay. So, how are we going to work out the average power generated by force F? Well, how much work is done in moving from point A to point B? It says the total work done by force F that moves the vehicle from A to B in 90 seconds is that amount of work. So it does that amount of work. And so if we've got work and we want to calculate power, surely we just take work divided by time and we get power. I would say that's just how simple it is. So we've got the work done by the force, work, divided by the time, which is 90 seconds, gives us the power. I think that's as easy as it is. The speed of the vehicle when it reaches point B is 25 meters per second. State the work-energy theorem in words. Use energy principles to calculate the total work done on the vehicle by the frictional forces. So what is this? It says mass starts from rest. Okay. So we know that it's starting from rest, and then it ends up at a speed of 25 meters per second at point B. So let's use energy principles to calculate the total work done by the vehicle by the frictional forces. So we're going to choose a formula. We've only got two to choose from. If we're working out friction, why not use the formula work non-conservative equals change of potential and change of kinetic. So kinetic energy is half mv squared. It's got none at there, and it ends up going at 25 meters per second. So we can work out the change of the trolley. It's going to be a half times this mass times its final velocity of 25 meters per second. So there's your change of kinetic. Then our change of potential is it goes from 0 height to 200 meters height. So change of potential is mgh final minus mgh initial. Its initial height, its initial potential energy 0. Its final is mg mass, that 1,500 times 9,8 times 200, and then you get its change of potential. So using that formula, work non-conservative is change of kinetic plus change of potential. You add the two, and it gets the work done by the frictional forces. Work non-conservative, yeah, that's frictional force, is change of kinetic plus change of potential. And there, that looks easy enough. And then finally, 2017's question on the work-energy theorem. This looks like a Newton 2 problem. A 4-kilogram block lying on a rough horizontal surface is connected to a 6-kilogram by a light inextensible string. State the work-energy theorem in words. The net work done on an object is equal to the change in its kinetic energy. Just rephrasing, work net equals delta K in putting it in words. The net work done on an object in an isolated system is equal to the change in its kinetic energy. Look at the definitions. When the blocks are released, the 6-kilogram block falls through a vertical height of that. Draw a free label diagram for the 6-kilogram block. Okay, what are the two forces? Tension and gravity. Force of tension in the string, force of gravity. Calculate the work done by the gravitational force on the 6-kilogram block. So work done by gravity, right? What's the work done by gravity? M times G times H. So you're going to get the change, you get the work done by gravity, M times G times H, or change of potential energy. I don't think there's anything more than that. The coefficient of kinetic friction between the 4-kilogram block and the horizontal surface is 0.4, right? Use energy principles to calculate the speed of the 6-kilogram block when it falls through 1.6 meters while still attached to the 4-kilogram block. So we've got a coefficient of friction, which is 0.4, and that's between the 4-kilogram. So could we work out kinetic friction here? What's kinetic friction here? It's going to be mu normal. What's the normal? mg. So 0.4 times 4 times 9,8 is going to give us the kinetic friction. So that acts backwards. How are we going to work out the speed of the 6-kilogram block when it falls through 1.6 meters? Okay, so let's just look at the system. The system as a whole has got two forces acting on it, really. It's got weight and it's got friction. So we can work out the work done by the weight is mgh. That's the positive energy given to this, mgh. The negative energy is going to be the friction times the same distance, because as this falls 1.6, this is going to be dragged 1.6. So if we take the friction, which is mu normal, that's the force, 0.4 times 4 mu times 9,8, and we multiply that by the distance. So we got the frictional force, we work out the frictional force times 1.6. We take that as negative energy. This is positive energy. So if we say change of kinetic energy, so what is using the work-energy theorem, right? That's when they say use energy principles, they say use one of those formulas. So let's just say we take the work-energy theorem, which is work net equals change of kinetic energy. So if we find the change of kinetic energy, we'll be able to find the speed, okay? And so the speed starts from naught. So what is the net work done? It's this work, that's positive work. So we're going to say m times g times h, and it's going to be cos 0 plus this frictional force times 1.6, and that's going to be times cos 180, because this is negative. We add those two, we're going to get the change of kinetic energy. What's the change of kinetic energy? It's half mv final minus half mv initial, and so we're going to be able to find out using that work-energy theorem, we're going to be able to find out what the change of kinetic energy was, and then what the change of velocity was after everything is moved. So the only trick here, I would say, is there's your one energy, that's positive energy, because it's in the direction that everything's moving. There's your negative energy. Both, the trick is they both get dragged the same distance, which is 1.6 meters. So that looks doable. And that was 2017. I must say this was probably the most challenging kind of question. The rest look all just fairly easy. And I'd say the only thing we've got to be very careful of is our positives and negatives. I like every work to have a cos theta to it. If you're doing work, is it going in the direction that you're going, or is it opposing the direction you're going? If it's going in the direction, it's positive work. If it's opposing, it's negative work. And so that's how you would do it. So all of these we've just gone through. We're not doing them for you. We're just showing you the principles on how to do them.